Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm very happy that we have Anvesh here to give us a talk this morning and to run through the gauntlet of the whole postdoc interview process. So he's about to finish up his PhD at CMU, working with Ed Clark. He's been doing some stuff all over the, well, not all over the place, but in model checking, mostly compositional, in bioinformatics, and I mean a bit longer ago, and also some stuff with probabilistic systems and statistics. So I'm really curious to see what happens now, because this question is entertaining. Take it away, Anvesh.
Thank you very much for the introduction, and thank you all for coming, and thank you very much for inviting me over here. It's true that I've worked on several things, but I will be focusing on just a couple of things on the slides today. So I want to talk about the question which is on the slide. Can you convince me why your software works? Okay. First of all, why bother? For one thing, software development is not about me and my software anymore. It's we and our software. Right? It's becoming a team effort, and it's always been, but it's becoming more and more nowadays. And we all know how hard that can be, especially when the documentation that's available is only informal, which is most of the times not even available. And it's great when things work out, but when they don't, it's the same cycle all over again. And this is not that far an exaggeration from reality. On the other hand, software can be very critical with pieces of our lives, parts of our lives depending on it. And the sad part is unwanted things only happen when we don't expect them. That makes it very hard to detect and fix bugs. And here is a bug discovered in April, which is part of a widely used open source network software. Forbes magazine says it's the worst vulnerability since the internet. So what was the fix? According to Wikipedia, the fix is to ignore request messages that ask for more data than their payload needs. In simple terms, it's a buffer overflow error. Apparently, the part of the code that contained the bug wasn't reviewed enough, but what this says is even seemingly simple bugs are hard to catch. And where social processes are weak, the mechanized skeptic is the more valuable, as Donald Mackenzie says in his book about mechanizing proof. In other words, one way to attack this problem is to use the machine itself to try to find bugs or prove their absence. And that's been the focus of my research in the last few years. And in particular, I've been working on automatic verification techniques. So today, I will first talk about analyzing program correctness in an automatic fashion, and in particular, how we can use the state-of-the-art solvers we have today for satisfiability, both for propositional logic as well as for first-order logical theories, also known as SAT modular theories or SMT. I will then discuss some exciting future directions for program verification. And finally, engineering a piece of software isn't just about getting it right, and I will describe some of my interests beyond program correctness as well. Mechanized verification has a very rich history, beginning with manual deductive verification and automatic techniques and techniques for trusting the results of verification. And beginning with the 90s, we have seen a rise in automatic techniques, scaling them beyond just simple toy programs and systems. And in particular, in the last decade, we have seen significant rise and breakthroughs in solvers for satisfiability, both for propositional and first-order logic. And today, I will be talking about some techniques for making efficient use of these wonderful solvers. But first of all, what is the intended output of verification? I'm sure you all know, but let me just clarify what is that I'm trying to do here. proof of correctness. This goes back all the way to Turing and von Neumann and has later been formalized by Floyd and Hoare. And here is a very simple flowchart program from Turing's paper in 49. And here is the specification, which is a relationship between variables you want to check holds whenever the program terminates. A proof consists of a bunch of assertions at various program locations such that they can be locally checked to hold. For example, if we assume this assertion before this box of statements, then we can show that these assertions hold after the statements. And the tricky part here is to come up with what is known as a loop invariant, which is something that holds at the head of the loop no matter how many iterations you take through the loop. Right? And here's a very simple concrete example. Here is a program, and here is an assertion which says x is non-negative, and that holds for all iterations no matter how many iterations you take. And the important thing is we only need to come up with a sufficient over-approximation that helps us prove the assertion at hand. And when we have procedures, we also need to say how the inputs are related to the outputs, using which we can again locally check that the assertion holds. And again, the idea is to come up with a sufficient over-approximation that helps us prove the assertion. So with that in mind, here is the concrete problem I'll be talking about today. Suppose you have a sequential program, P, and some safety assertions. The goal is to automatically verify for assertion failures, either output a proof of safety or a counterexample. But because of undecidability, we also have a third possibility where we say we run out of resources, but here are some useful facts. Now, what do I mean by useful facts becomes clear as we move along. Now, one way to address this problem is to...
So, what class of safety assertions are you going to allow? I mean, you could have a lot. You could be memory safety or security, or it's a big space there.
Right.
What class are you dealing with?
So the algorithms I'm talking about are general, but the implementations we have done are specifically for arithmetic properties, and we are currently working on memory as well. So I'll be talking...
So
I won't be focusing on memory in this talk,
right.
But these are generic
limited
techniques.
Initial space. There's
Right.
a lot of other properties we might like to
Right. These are generic techniques modulo the underlying theory. Right. So one way to address this problem is to incrementally consider reachable states. For example, start with the initial states, check that they are safe, and look at states reachable in 1 step, 2 steps, and so on. But even though we bound the number of steps, the reachable states can be infinite, right? Or practically infinite if you look at, if you consider the machine limitations into consideration. But fortunately, we have efficient solvers today for satisfiability, and we can use them by using a technique called bounded model checking, which I'll be describing shortly. But how are we to find a proof of safety if we are always within the reachable states, right? The goal is to find a safety proof that separates the reachable states from the bad states. And that brings to the idea of generalizations, where after we have proven safety for a particular value of the bound, we generalize what we have seen, right? And this can be done using techniques based on interpolation. So if we generalize after checking safety for every value of the bound, the hope is we converge to a safety proof, right? That includes all the reachable states and separates it from the bad states.
And you know when you've reached one.
If we have reached, we can check that we have reached, assuming you have an oracle for SMT again. So here is the high-level picture of what we've seen for SMT-based verification. Each iteration, you fix a bound on the reachable states, you check safety using bounded model checking, and you either get a counterexample or a bounded proof, which is a proof that proves safety of the particular subset of reachable states you've seen so far. And then you check if you've converged. Is the proof really dependent on the bound or independent of the bound? If it is not independent, then you continue the next iteration, consider the next subset of reachable states, and so on.
Where's the generalization step in this picture?
It comes out in this proof. So bounded model checking does Here I'm assuming that it does safety and also generalizes.
Okay, so it's inside the.
It's inside this box.
Okay.
Yes. This is great, but existing techniques for bounded model checking are inefficient in the sense they create large formulas that can grow exponentially for programs, and I'll be describing shortly why. And because of undecidability of the problem, this loop doesn't always converge. So how can we deal with divergence in practice? So we try to address these problems using compositional reasoning, which at a high level says, break down the question of the entire program into questions about individual pieces that can be analyzed locally. In particular, I will describe two techniques. The first one is a compositional approach for bounded model checking, and I'll be focusing on procedural programs, possibly recursive ones. And the second technique brings in ideas from abstraction refinement into the context of SMT-based model checking, and I'll be focusing on loopy programs, where you have a single procedure, but you can have all sorts of loops. So let me begin with the first technique. To understand the importance of compositionality, let's first look at how traditional bounded model checking works. So here is a simple example I've shown you before. Now, the idea of bounded model checking is to bound the number of iterations of the loop, say B, number of iterations, and create a formula that symbolically represents unrolling the program on the left for B iterations. So here x0 is the value, denotes the value of x initially, and each xi denotes the value of x after I iterations. And after B iterations, we exit the loop, we flip the sign according to this statement, and then we negate the assertion for the final value of x. And the idea here is this formula is satisfiable if and only if there exists a counterexample of B iterations. Now, for procedural programs, the bound is on the recursion depth, or more generally stack depth if you have multiple procedures. And here is an example program where you have a main procedure and a bunch of level procedures indexed by a number I. Main makes 2 calls to level 1. Each level I makes 2 calls to level I plus 1. And let's say level n doesn't make any calls to other procedures. And here is how an unrolling might look like for this program for n number of level procedures. Right? So main makes 2 calls to level 1, and each level I makes 2 calls to level I plus 1, so we get this tree structure. So here I'm using B10 and B11 to denote the input value and the output value of the parameter B. Now, the thing to note here is the size of the unrolling grows exponentially in the number of procedures, n, right, which happens to be the size of the program.
As does the execution time of the program.
The execution time is satisfiability of this formula, which can be exponential.
The execution time, not of the model checking, but if I ran the program, it would take exponential time as well.
No.
No? Oh, maybe I'm missing something.
The Boolean flips every time, so you only do one of the 2 level calls.
Aha. Does it now? Level I called level I plus 1 with B, it doesn't flip anything. It looks exponential to me. Is execution time exponential as well?
Execution time can be exponential. Yeah.
Okay. So then it arguably it might not be so bad if it takes exponential time to verify an exponential runtime program.
Right,
Maybe.
but it is surprising because we know of polynomial time algorithms. Right? Especially when the program variables are Boolean. And now these algorithms are not SAT-based. For example, I'm referring to bebop, for example, here. And they're not readily extendable to non-Boolean programs. So what can we do? So this brings to our key ideas, where we say that instead of creating these large formulas for the entire program, break down the question and analyze procedures individually. So we create what are known as reachability queries for individual procedures. So here a reachability query denotes a formula describing a set of states that we don't want to reach. And to do that efficiently, we need to maintain approximations of procedure behavior. And in particular, we maintain 2 kinds of them, under approximation and over approximation. And I will describe shortly what I mean by these. But these two ideas are enough to improve the complexity to polynomial time when you have Boolean programs. And in general, for arbitrary first-order theory, if you have an SMT oracle, we show that this approach terminates for a given value of the bound, despite the non-trivial compositionality of the algorithm. And the over approximations here are essentially the generalizations I was showing in the Venn diagram. Now, these ideas utilize or create formulas that involve auxiliary variables. And in order to be efficient, we need to avoid depending on these variables. And I'll be describing model-based projection for practically dealing with eliminating these auxiliaries. But first of all, let me show you the high-level picture of our approach. So suppose you have a bounded reachability query for a procedure P. In other words, you have a formula describing a set of bad states you don't want to reach, and you're asking, can I reach those bad states? And you also have a bound on, in this case, the stack depth. We first try to locally answer this query by utilizing known approximations under and over of the procedures we are calling. And if they're not sufficient, we need to update the approximations. And we do that by creating compositionally new queries for the procedures we are calling and update their approximations and iterate this process. So let me describe each of these steps in the next few slides. First of all, what do I mean by these approximations? So suppose I have a procedure foo with an input x, output y, and the procedure has two paths, right, based on a condition whether x is positive or not. I say that this formula is an under approximation of foo because every SAT assignment of this formula corresponds to an actual execution. In this case, this corresponds to the then branch. So it says if x is positive, I increment it twice and assign to y. So that means y is x plus 2. So that's what this is. On the other hand, this formula is an over approximation because every execution of the procedure satisfies the formula. Right? In this case, the else branch can be summarized by simply negating the if condition, and that is the first disjunct. And the then branch says if x is positive, y has to be positive as well. So that's the second disjunct. Now, how do we find these approximations automatically? So I'll be describing using an example. So suppose you have...
So I'm just struggling with these under approximations and over approximations. Can you go back a slide? Right. So x begins 0. So the x is an input and y is an output. So it's kind of like if the precondition, if I think of x greater than 0 as a precondition, then y equals x plus 2 is a postcondition.
Right. So
but the second one doesn't look quite the same because it has an or in it.
Right. So here these are.
Do you think in terms of preconditions and postconditions?
So over approximations can be expressed as pre and post. So you can say so these are essentially relations. We are expressing these as relations. So if you want to say if you want to express it as pre and post conditions, the way to do it is we are treating this as so what we do here is we have, so if I can.
Don't get stuck on this.
Right. So what I'm saying is we are essentially looking at describing these approximations as relations between inputs and outputs. So as a precondition and postcondition, it becomes essentially you introduce specific auxiliary variables denoting the input values, and the postcondition denotes how the inputs are modified or how inputs are related to the outputs.
I think in this case you could say true for input and use that as an output. Yeah. So true for preconditions,
Right.
I could do that.
Right.
But you're saying it's more helpful just to think of this as a relation, and the under approximation is smaller than the actual one.
Exactly.
And the approximation is bigger.
Exactly.
Fine. Okay.
And we can express this as pre and post conditions using auxiliary variables, because more generally, if the variable is modified, we can say here is the initial value, let's say it's x0, and how does the final value relate to the initial value? And, all right. So let me explain how to infer these approximations using this example. So suppose you have 3 procedures, and suppose we know already some approximations, which I've labeled here. So let's say for foo, we really don't know any approximations. Under approximation is false, over is true. And for bar, let's say we know this under approximation corresponding to the then branch of this if condition, which says if x is greater than or equal to 5, then y is x plus 1, right? I know that. And I don't know anything about the other branch, let's say. And the over approximation says no matter what branch you take, the absolute difference is at most 1. And similarly, we know some approximations about Baz as well. Okay. So suppose we know this already. And now let's say we have this reachability query for foo, which asks, is there a path in foo such that the output z is greater than the input x? Okay. Now we can answer this readily using approximations and say, oh, I know these approximations about bar. In particular, I know that there is a feasible execution in bar that satisfies this under approximation I have over here. I can just instantiate this in terms of the actual parameters here. And similarly, I can instantiate this with y and z. Right? So I know that there are executions in bar that are feasible satisfying these conditions. So in particular, I can use this to say, oh, if x is 5, I can go to 6, and then I can go to 7. And 7 is greater than 5, satisfying my query. So note that I didn't have to look inside bar. I just had to use the approximations I already know. So now I can update the under approximation of foo and say, oh, I've got a new point, 5 and 7. Right? But this is very specific, and this is not going to scale if you just look at concrete values of the variables. But fortunately, we can do better than this.
So this under approximation is maintained as a set or something, or
As a relation. As
a set of under approximations, or
it's just one formula.
It's just always one formula.
Yeah, we keep conjoining things to it.
Then that could also blow up, right, in size exponentially. Because
It's going to improve it right now.
sorry.
It's going to improve right now, this way of adding points.
But it could explode exponentially, right?
I mean, the size can grow, but whether it's exponential or not, I mean, if for example,
Paths, then if I just compute the symbolic constraints, one for every path, then the under approximation would be exponential, right? So.
if you look at the number of paths, but if I'm looking at, right, I mean, exponential in what? Exponential in the number of variables, or exponential in the, so if you look at this for Boolean programs, for example, it's linear in the state space. The state space is exponential in the number of variables.
This formula size could explode. I mean, unless you use a simplification or something, right? If I just naively just...
Right, but if I simply look at, simply add points that are reachable, then I can only be as bad as the number of states, number of actual values of the input outputs. Right? So if there are b variables, b parameters, then I can only have 2 to the b points.
But you can still have an exponential formula, exponentially sized formula.
Right, but this is polynomial in the number of states. Right, yeah. Yeah, the formula size can be exponential, but I'm saying it's only as big as the number of states.
Okay, that's pretty big.
Yeah.
I mean, yeah, but that's still better than what we have today. But in general, what I'm saying is that's what happens if you maintain them explicitly, but we maintain them symbolically. So what I'm saying is, in particular, you don't have to look at the specific concrete points, but you can look at the path condition. And in particular, if you look at the path that goes to the then branch, then we can simply look at the under approximations we have for bar, and we can simply conjoin them and say any pair of values of x and z that satisfy this is feasible inside foo. And in particular, this includes 5 and 7 and possibly many other points as well. Right? But now we have added some auxiliary variable y, which is not is neither an input nor an output. So we need to quantify it out. And
so unlike typical approaches which use summaries, your approach here, or at least what you describe over here, doesn't seem to use the calling context, right?
So the calling context comes into play when we look at how queries are created. So let me show you using another example. So how we deal with these quantifiers, I'll be describing shortly. But suppose we have a different query now, which says z is less than x minus 5. So now under approximations are not enough to show reachability, but we can use over approximations to show that it is not possible at all, no matter what you do. So here I'm instantiating.
So was the previous query a reachability query? Previously we were checking.
So previously we were checking z is greater than x.
Reachability.
Right.
Okay.
We're always checking reachability.
So that's fine. Okay.
Right. So now we are checking.
Something different about this query.
It's a different query.
Oh, yes.
It's a different query, and I'm showing that the under approximations are not sufficient. We cannot.
What's the difference? Why was it okay before but not now? Why was under approximation enough before, but not for this new query?
We can check whether we can show reachability using this or not. I'm saying.
You could just say, do the algebra, it doesn't work.
Doesn't work,
Okay.
yeah, right.
Okay, whereas it did before. Okay.
I think it's just given the other approximations you had, you couldn't show it.
Yeah.
Yeah.
These are just examples.
But
Also, for any reachability query that isn't actually true, no under
Yeah.
approximation.
Aha, that is a good answer.
So you can do the math.
I see. So we're using under approximations to prove that the reachability query is definitely true, and over approximations to prove that it's definitely false.
Right.
Okay, now you're cooking with gas.
Okay. Right, but all we can say using under approximations is here, we don't know. Right? But using over approximations, we can say this cannot be reached. Right? So in this case, here are the over approximations we already know, which says the absolute difference is at most 1. We are just instantiating it. And here we're instantiating this over approximation. And we say that no matter what branch you take, if you take the then branch, z is at least x minus 2, so it cannot be less than x minus 5. If we take the else branch, z is at least x, so it cannot be greater than x minus 5. So using over approximations, we can show that this cannot be reached. And now we can update our over approximation by simply, say, negating the reachability query. But we can do better than this by using interpolation techniques, and I won't be talking about this in detail. But what if you have another query where existing approximations are not sufficient? And again, I'm not going to show why, that we can do the math, but let's say the approximations are not sufficient. But we do have reachability using over approximations in this case. So we know that no matter what Baz does, z is greater than or equal to x. And if this is all we know, then we can go from 1 to 2, and 2 is 1 plus 1. But the question is it really feasible in Baz? So we create a new reachability query for Baz, looking at what's happening along this execution, assuming this over approximation, and ask Baz, can you really have an execution where your output is input plus 1? Right. So this is where the calling context comes in. We look at the abstract counterexample to see what is that we need to know in order to show feasibility of the counterexample. And we can analyze Baz in a similar way using approximations.
Right. So if we find something we can't either prove that it's definitely true or definitely false,
right, then we need to
then
update
you
the
have a
approximation.
choice about whether we try to improve the under approximations of our callees or the over approximations of our
Right.
callees. How do you make that choice?
So we make queries. So we know that there is at least one procedure call whose approximation needs to be updated, and we essentially ask what is that it needs to be consistent with. So we look at the calling context, all the other procedures or other constraints along the path, and say, are you consistent with these other things, such that I can reach this query? So I just ship off a query, and when the query gets answered, it gets answered either positively or negatively, and then we know what's happening. Right. So it's all done.
So you don't have to ask two queries.
You don't have to
One
ask two
okay.
questions, yes. So I'm asking, are you reachable? Can you reach this query? And it comes back either yes with an under approximation or no with an over approximation.
Are you going to explain how you guess at the query?
Not in this talk, yeah. But I can explain it offline.
How is this related to the compositional May-Must analysis, for example, in Yogi and things like that?
Right. So there, so I don't think that is complete in the sense it's not, I don't think it has guarantees of termination because the under approximations there are based on testing, and it's a must. Yes, it's similar, but they don't deal with quantifiers the way we are doing in a complete way. Right, but you pick a test case and you run and you look at specific values, right? Or you do exact quantifier elimination, which can be expensive. Right. And the summaries are different in the sense you also have ghost variables in that procedure, where we only have parameters, formula sort parameters. And
The summaries are exactly the same. The formulas, they're defined over parameters. You don't have any ghost variables.
Right. But if a parameter is getting modified, for example, you don't have a relation between input and output. You say, if this is the precondition, this is the postcondition, right? And that can blow up, for example, if if I have a variable that is not, I mean, we can discuss this offline, I guess. Yeah. So here is the picture. I've tried to describe each of the steps in the last few slides, where suppose you have a reachability query, we first try to use existing under approximations, the procedures we're calling, and see if we can answer reachability positively, or use over approximations if we can answer negatively. And if neither happens, then we need to update the approximations by compositionally creating queries. But now let me come to the question of how to deal with these auxiliary variables. So suppose you have this quantified formula where you're interested in x, but you also have some auxiliaries L, which you need to eliminate. So how can you do this? Well, if we have algorithms for quantifier elimination, which compute equivalent formulas which don't have the auxiliaries, then we can directly use them. And for example, here's an example which says there is a y between x and z is the same as x is less than z. Right? But unfortunately, these algorithms have very high complexity, especially if you have integers. And moreover, if we always eliminate auxiliaries in an equivalent way, that amounts to exact reachability analysis, and that's not going to scale in practice. So how can we eliminate quantifiers approximately? And let me consider the specific case of obtaining under approximations. So suppose you have a path condition using some under approximations over the pre and post parameters, and suppose you have auxiliaries L, that is consistent with a reachability query. Okay, suppose you have this situation. Now the goal is to find an under approximation of the quantified formula which doesn't depend on auxiliaries, which is also consistent with the reachability query. Right. Now we can simply pick a specific point, like if x is 5, then input is 5, output is 7. But can we do better than this? Right. So that brings to the idea of model-based projection, where the high-level idea is following. Suppose you have this circle which represents the space of all values of the variables x that makes this quantified formula true. Now, instead of generating one formula that covers the entire space, the idea is to come up with a formula that covers a subset of the space. And if we can have a finite decomposition, then we are not losing on completeness either. We will eventually generate all the subsets. And the idea is to generate the subsets using a model. So suppose you have a model which is an assignment to all the variables x and L that makes phi true. And suppose here is where the projection onto the x variables lies. The idea is to pick that subset that covers this particular model.
So just say that once more. I understand what n is. Then you said something about the projection onto.
Right. So we are looking at the x variables, right?
Yes. Okay.
So M assigns values to all x and L.
Yes.
So let's look at what the assignment to the x is.
Okay.
Okay. Let's say this is where it lies.
This is what?
This is where the point lies in the space.
But the grey space is all assignments to x.
Yes. And this is where that particular point is.
So you get the rest of the freedom from
So-
assigning to L.
So let's say M assigns x to 5 and L to 7.
Oh, you mean
Okay.
in the purple space, all the assignments to x are the same.
No.
They
I'm not-
vary.
I'm not-
The
no.
m varies only in assignments to L.
No, I'm not saying
no,
that.
that wasn't right either.
So I'm saying that suppose this is a space of all values of x that makes this quantified formula true.
Yes.
And here I know that say x is 5 and L is 7 makes phi true.
Yes.
So that is what M assigns.
Okay.
And let's say x equal to 5 lies somewhere here. Let's forget about L.
Okay.
Okay?
That's the black dot.
That's the black dot.
Okay.
And the other dots in this subset can be other values. Say maybe 1 is also here, 3 is also here. But I'm saying that find some subset which is more than the point, which consists of other points as well,
Okay.
that includes this point.
Oh. Okay. Any subset that includes that point.
Any subset,
Okay.
but I'm saying that if we can do this using a finite decomposition, if we can only manage to get finite subsets, then we are not losing on completeness either. We will eventually cover the entire space. Right? And how we do that, I'm going to describe that shortly. In fact, I'll just do that using an example. So suppose you have this quantified formula in, let's say, linear rational arithmetic, just to keep things simple. So all the variables are rationals or reals, and we only have linear arithmetic here. And we want to eliminate this auxiliary L. Now, we can show this equivalent formula, which doesn't have L, and this can be obtained in particular using the quantifier elimination algorithm by losswise Fenning. So let me just illustrate what each of these disjuncts is at a very high level. So the first disjunct corresponds to the case where the equality is true, like L is equal to E, then we can simply substitute E for L in the formula. And the second disjunct corresponds to the case where the lower bound is true, and the third disjunct when neither is true. Okay? I'm not explaining how these are obtained, but there is an algorithm to obtain these disjuncts. Right?
That's this doubly exponential quantifier elimination algorithm.
So for reals, it is exponential. It's not doubly.
Okay.
But for integers, it's doubly exponential. Right?
Okay.
Okay. Now, the idea is instead of generating this entire disjunction, the idea is to use a model to pick one of these disjuncts. Right? So if the model satisfies equality, pick the first one. If the model satisfies the lower bound, pick the second one, and so on. So that's the idea. I'm not describing the entire algorithm here, but the idea is to look at the model and pick the disjunct where the model corresponds to.
A satisfying assignment, a model.
You find a model,
Okay.
and
so
then you
don't do that
identify.
to start with.
And then you identify which disjunct covers that particular model, and pick that disjunct. Okay.
So assuming you found all the disjuncts.
Sorry?
So you found all the disjuncts.
We don't find all the disjuncts. There is an algorithm to directly find the
Oh,
disjunct.
okay, the appropriate disjunct.
Right.
Oh.
We don't need to generate all of them at the same time. Right? And in the future, if you get a different model, then you get a different disjunct. Right? And we make sure that we don't find the same disjunct twice, so we don't have redundancies. So this is all I want to say about model-based projection. And
Sorry, so how did the complexity decrease due to this? I didn't understand that part. So,
I didn't explain the complexity yet.
previously.
Uh-huh.
So how does this help reduce the complexity?
This doesn't reduce the complexity. This is just a practical heuristic.
I mean, you lazily explore the complexity. You might terminate before actually generating the...
Right, but in the worst case, I might generate all of the
But in the
disjuncts.
worst case,
Right.
yeah.
So this is not for reducing complexity. This is just for practically dealing with quantifiers. Okay. So coming back to this picture, we can now substitute the compositional approach. In
How this works in
Yes,
practice?
yes, yes.
And how does it compare with Z3, for example?
Yes, I'll show shortly. Right, so now we can substitute the compositional approach in place of traditional bounded model checking. And we can show that this terminates as long as you have an SMT oracle. And this whole loop terminates for Boolean programs, and this is polynomial time. And the high-level idea is there are only as many approximations as there are reachable states. And each iteration refines at least one of the approximation. So that's the high-level argument.
There's an exponential number of reachable states, even for Boolean programs, aren't
Yes, I'm saying polynomial in the reachable states.
Okay. Which is essentially is infeasible in practice.
Well, depends on what you mean by infeasible.
Time in something that's larger than the number of protons in the universe is not going to be helpful to me, is it?
But it's still better than existing approaches, is what I'm saying.
Okay.
The number
So-
of states in a Boolean program is potentially very small compared to the number of states in an actual program.
Well, it depends on how many variables you have.
Often you can get away with
Yeah.
But when you say better, hopefully you're going to justify it with some empirical results, right? Comparison with bebop or
Right here. Next slide, actually. So here is, we have implemented these algorithms in our tool called Spacer. So we have a C program, and there's a front end based on a compiler framework, LLVM. We compile that into intermediate form, SMT-lib, and I guess people here know the Horn class format. So this is the Horn class format. And then we feed that into Spacer, which implements these algorithms. And here is a comparison with Z3 on the Boolean program I showed in the very beginning, which has exponential unwinding. Sorry?
Is this PDR or?
Yeah. And we see that as we increase the number of procedures, Spacer can handle the increasing complexity more gracefully. And we have also done controlled experiments to see the individual advantage of the techniques, specifically model-based projection here, where we see significant improvement, as well as addition of under approximations.
Which category is this?
So these, I believe, are the these are the control flow integers, device drivers, and those categories.
PDR is not in the top 5 in that competition, probably. How do you compare with?
Well, the point of these is to show the individual advantage of these techniques. Right? I'm not saying Spacer is the best, but I'm saying these techniques really add value. And here is the slides we show.
Comparing a pretty different algorithm to PDR, so you're not comparing just one little technique. You're
No, actually, the key difference between Spacer and PDR, Z3 PDR, are these two techniques, MBP and under approximations. If we strip them off, it looks very similar to PDR, and we can discuss that offline. So what we have seen so far is a compositional approach for SMT-based model checking, where approximating both the feasible and the infeasible is important. And we have also seen model-based projection for obtaining cheap approximations. And the idea is full quantifier elimination may not be necessary in practice. And it's interesting to look at other theories like nonlinear arithmetic or uninterpreted functions, for example.
So what about comparison with other program verification tools that participated in the SVCOM?
Right. We haven't done those comparisons yet. Okay, so let me quickly explain the second technique, which tries to bring in ideas from abstraction refinement into the context of SMT-based verification. So let me check. Do I have like 10 minutes or what's the time?
Like 10 minutes, yeah.
10 minutes, okay. All right. So let's consider this program, which has this assertion, and we need to check this assertion. And we tried this program on Z3, the PDR engine, and we cannot verify it in an hour. And here is a loop invariant, which is useful to show the assertion. Right. So let's see. So if you look at what Z3 is trying to do in terms of the bounded proofs, it never really connects the variables z and w the way we want it here, right, to show the assertion. In fact, it produces things like after one iteration, w is 1, z is 10. After 2 iterations, w is 2, z is 20, and so on. So even though there is an implicit connection, it doesn't really find it. So on the other hand, here is a very simple abstraction of the program which says, let's say t gets an arbitrary value. Right? The same tool can verify the program in less than a second.
What is that?
So it's apparently finding connections because now t is not a concrete value. So it says w is t, z is 10t, and apparently it's doing some resolution over t. And so being symbolic seems to help. And as we all know, abstractions only add behavior, so it's conservative. And the question is, how can we automatically find abstractions? And in the interest of time, I will skip some of the details and let me explain at a very high level what we are doing here. So at a very high level, the picture is the following. So SMT-based verification explores under approximations, like different subsets of reachable states. What we are doing with, or the idea we have here is to come up with abstractions and add a new dimension. So let's say we prove initial state safe. Then instead of looking at states reachable in one step, we look at an abstraction of the reachable states of up to one step and iteratively refine it until we come up with a suitable abstraction using which we can show bounded safety for that value of the bound and continue this process until we get this. So the idea is to use the proofs to obtain abstractions so that you can use the abstractions for checking safety of more reachable states. So instead of looking at the original program, we want to look at the abstractions.
In your example, is going symbolic on t, is that the abstraction?
That's an example. Okay. But we have a different kind of abstraction as well, but I do not have the time to explain that.
How is the difference from the CGAR-based tools?
So CGAR only looks at abstractions and tries to refine it. And the idea there is, or the main assumption there is, you can get an abstraction which you can decide, whose correctness you can decide. Right? For example, you can use predicate abstraction to get finite state abstractions, and you can use any BDD-based model checker or any other model checker which is known to terminate and give a value. Right? But here, we are not necessarily confined to finite state abstractions. So you cannot get an abstraction and ask another model checker because that's not guaranteed to terminate. So we have this fine-grained integration between abstraction and SMT-based verification. And I can describe that offline. Yeah. So let me just say that, okay, so showing the results probably doesn't really help without explaining the technique. So in the short time I have, let me just describe some of the lessons we have learned, I've learned here. The first is compositionality is key to scalability, both in theory and practice, and it improves the complexity as well as we see the advantage with realistic examples. And heuristics continue to be important to get practical implementations, and we have seen that with eliminating quantifiers. And there are also questions like when is the right time to define an abstraction. And in all that, we have seen a hierarchy of automatic decision procedures. So we know SMT has been influenced greatly by heuristics from the SAT community, and today I've described one technique, 1.5 technique, for inferring invariants using SMT solvers. And these come under the category of quantifier-free invariants. And it's interesting to look at how we can extend these to more expressive invariants, and in particular, how can we find quantified invariants. And moving on, there are many interesting directions for future exploration, and here are some of the ones that interest me the most, excite me the most. For example, for one thing, today's verifiers and software model checkers, they are primarily single core implementations. And I think it's time to move distributed. For example, we can exploit compositionality, as I've been describing. We can analyze different pieces on different machines. We can exploit non-determinism in algorithms. And today's algorithms have many different features, and they make specific choices in their implementation. But we don't have to. At a high level, proof finding and bug finding need different techniques. And this also helps with better memory management to scale to larger and larger programs. Another direction is to augment verification with synthesis techniques. Synthesis is the flip side of verification, which, given a specification, tries to synthesize a code fragment that is guaranteed to satisfy the specification. And we can use that, for example, to synthesize terms useful in invariants. And this is especially important for more expressive invariants like quantified invariants, where you need to find appropriate terms to make the problem more feasible. Synthesizing ghost code, which is a piece of code whose main purpose is to assist verification and not interfere with the execution of the original program. And we see that done often in manual deductive verification, but we don't see that in automatic techniques. And combining with domain-specific synthesis techniques, and we are seeing a rise of those techniques, for example, synthesizing regular expressions from examples, or data structures from relational representations, and so on. So how can we leverage the advantages of both synthesis and verification in a seemingly integrated fashion? And finally, when exact verification is hard to scale, how can we deal with that using approximate techniques? And I've done some work on probabilistic correctness guarantees on finite state systems. But it's more interesting to look at realistic infinite state programs, right, where you have integer variables and so on. And I think we need new deductive systems and logics, and this is something significantly underdeveloped, in my opinion.
What would such a new deductive system or logic tell you? Can you give an example of what kind of thing you have in mind?
Like, for example, an approximate variant of Hoare logic, right? So what is an invariant, which corresponds to a probabilistic guarantee? And how can we fit things in a compositional manner? Right? I have invariants, probabilistic invariants for one piece, another piece. What does it mean to compose them? What's a good proof rule?
What's a probabilistic invariant? Something that when you say it's probably true that X is bigger than
right.
Y.
Some assertion is true with probability 90%, right? And some assertion is true for one component and have different component with such a guarantee. And how can I combine them into a probabilistic guarantee about the composed system, for example? So what's a good logic for that?
This is at variance with the point you started with, which is that we really want to know. There's some programs we care that they're absolutely correct. Like you started off with Heartbleed. So.
Right, I'm saying that when it's hard to scale, exact verification is hard to scale, can we at least get probabilistic guarantees? And
maybe. Yeah. I suppose if the probability was high enough, like, there's only one chance in 2 to the 50 that it's wrong, then I'd be with you.
Yeah, I mean, there are some very safety critical applications for like security, and Heartbleed might be one of them. And there, perhaps you don't want to take the risk of probabilistic guarantees, but.
Do you have any examples of what a probabilistic guarantee might look like? I mean, they're sort of existing. You cite some papers here, but.
I don't have an example on the slides, but.
I mean, existing systems where you feel they've made useful progress on this.
So the examples I have considered in these papers are when the programs themselves are probabilistic. So you have randomized protocols.
Oh, okay, then a whole different story. Yes,
right. But I'm generally talking about the case where you have, like, not necessarily randomization in your program, but you still want to have probabilistic guarantees about the program. I don't have examples.
Any prior work on that, or is this something that you just think it sounds promising?
There's work by Sriram Shankarnagan in the hybrid systems community and so on. A lot of work in this area.
Yeah.
Right. I guess it's okay. Right. I'll wrap up. So let me just say that, let me just take one more minute. And so moving on beyond correctness, here is the high-level problem I'm interested in. How can we raise the level of abstraction of programming to make it more intuitive and more easy to understand? And I think there are several interesting and exciting challenges here. For example, the moment we raise the abstraction, it becomes less formal, and we need to deal with a lot of non-determinism, these things. And I think I'm imagining some interactive system with interactive programming environment where you are dealing with this high-level intuitive environment, and you have a backend that is trying to synthesize a formal, precise program which can be run. And there are interesting challenges like what is the right HCI, human-computer interaction, for programmers themselves. And for this, I have this approach in mind, which is what I call compositional development of programs, where you're dealing with this high-level interfaces. And today we have lots of repositories of code out there. Some of them can be even produced by synthesis techniques. So how can we leverage all of this? And this is what I call crowdsourced programming. And we are getting there. This is not too far in the future. And so with that, I want to conclude my presentation, where we have seen some efficient techniques for SMT-based verification. And I see an exciting path ahead towards being able to convince me why your programs work. Thank you.